Hey everybody, we are Save the Knee. We're doing tech binding release force testing, and my name is Kai Kendrick.
I'm Riley Cairns.
I'm Dan Sturba.
I'm Jake Taylor.
And I'm Jacob Spicer.
All right, so our test objective with this experiment, we wanted to evaluate the release force characteristics of a tech binding, which is used for backcountry skiing, and we'll go into that in a second here. And we want to get accurate data, and we're comparing it to the alpine binding. So the alpine binding's on the top there, the tech binding's on the bottom there. And our key question that we're trying to answer is, are tech bindings safe? Because they're held to different standards than the alpine bindings. These standards are made by the ISO, International Organization of Standardization, and they're outlined by these two documents here, 9462, 13992. The first one is for the tech bindings, and the second one is for alpine bindings. These are determined by this institute on the top here, and they contribute to ISO. So the whole reason we're doing this is because there's obviously standardization here for testing, but there's not a whole lot of standardization for safety. And because of this, the tech bindings tend to be a lot less safer, and there hasn't been a whole lot of testing. And on top of that, so there is a standard, but most of the tech bindings in the industry don't even meet that own standard. And here to the right, we can see our boot sole length corresponding release settings. So this is basically how a ski shop would set your DIN based on your height and weight. Yeah.
So what is the significance of this testing? As Kai mentioned, these type of bindings don't have a lot of information around them. Not a lot of them are as standardized as a normal alpine binding. On top of this, the kind of skiing that people are doing with these bindings is a lot more dangerous. They tend to be in more desolate environments where if an injury does occur, it's a lot scarier than it would be at your local ski mountain. In the United States, approximately 600,000 skiing related injuries occur, with 30 to 40% being knee related. By looking at what we're testing in this study, we hope to narrow in these sort of forces and be able to reduce the injury caused at the knee with the torsional force.
So for our test, we'll be utilizing a load frame and putting the ski boot under a tensile stress, and we'll do that by basically bolting it into the frame of the load frame in two different ways that I'll explain next, and we'll put basically a ratchet strap underneath the bottom of it so that when the bed lowers, it pulls up on the boot and it pulls out of the binding. On these bindings, there are two different types of settings. There's your pin tension, which is set with a screwdriver in the back, and that sets your DIN. The bindings that we use are these Dynafit speed turns, and those DINs range from 4 to 10. There's another setting on the binding called pivot tension. There's no metric to measure that, so we had to turn a screw in the back, and we'll go into a little bit later how we measured that. But to mount the boots onto the bed load frame, we actually had to custom make brackets, mounting fixtures. And we did an FEA on this using SolidWorks. We assumed that there would be a upwards force of around 600 pounds on the boot. And we set the factor of safety to 2.0, and we found that there was no yielding, there was no excessive strain on the binding or on the fixture. So we're good to use them. Like I said before, we're going to be doing two different types of tests with these bindings. One is axial, where the boot gets pulled directly upwards, and then one is torsional, where the boot is put on its side, on those attached to those vertical plates of the fixture, and the heel is pulled up so that it twists out of the binding. You'll see in the results, but when we collect data and it twists out of the binding, we read that max force, which is our release force.
Of the equipment we used during our testing, a lot of the equipment used, we were able to use through the university. Some of the things we were, we'll talk about this later, but as you can see in the bottom of the slide, you can see the actual brackets we made. However, based on the last slide with the technical drawings, we had to make a few slight modifications to it because when we were actually creating the brackets, we had a couple mishaps with the dimensioning. So we brought it back to the university's machine shop and we were able to fix them. And then on the top of the slide, that's what the load frame actually looked like. It was a model 4505, and that was provided by the university.
Here is our step-by-step test procedure. We first secured our fixture to the load frame using bolts. We had 4 bolts, which were enough to meet our factor of safety standards. Then we mounted our ski bindings to our fixture. This was done using set screws right into our bind or after our fixture. Then we attached the ski boot into our bindings. At a set din, we started at the lowest, which was 4, and we worked our way up and worked our way back down. Once the boot is secured in, we ran the load frame at a consistent extension rate, which we'll talk a little later, until the boot popped out with the binding or released from the torque. And we collected the data and repeated this multiple times, identifying the max release force for each test, which we could then analyze. And then obviously we repeated this test for the alternate boot orientation on the side, pulling upward. Looking at the controls for our load frame was the Instron 4505, which uses the Blue Hill Universal 3 software. This allows us to control the extension rate, the force, and also collect the data pretty accurately with its load cell. We did a rate of 4 millimeters per second downward, which would pull the boot up. This is kind of standard for most rates of ski binding testings. We use the same boot and binding for each test, so it's kind of consistent. The test stop conditions were a release force of 200 newtons at 25% of that release force. So as you can see in the bottom with the graph, you can see that as the force is increasing, when the boot pops out, the force will drop down, and that will indicate the stop of the test, and the test will stop. And obviously before each test, and after we secured the binding with the straps, we zeroed the force and extension. That way we had consistent data.
So here's testing pictures and footage from our experiment. In the bottom middle is the axial force setup with the binding, where the pins are in the back and the straps are on the bottom of the boot, which pull up axially on it. And on the bottom right is the setup for the torsional experiment, where the boot is, as Dan mentioned, on the side, mounted sideways on the steel bracket. On the top left is the axial release in video. You can see it pulling straight up, and the second release is it pops right out. And on the bottom left is the torsional release. And even though it's not as sudden, you can see the ski binding on the far left there, rotating around and releasing as more force is applied. In the top right is the graph for one of the tests actually that was seen in the last slide with the release at around 800 newtons for that experiment.
We came up with when doing our experiment, we were able to bring a budget plan to Professor Hoover, which he approved most of the items. However, as a group, we all pitched in to pay for the actual binding set. When all was said and done, it was about $340. Cool. We stood by throughout the entire semester. Um, during the start, it was a lot of writing and brainstorming for how we were actually planning on testing the release force of the binding, and how we were actually going to build our brackets and figuring out the logistics of how we were going to test it. And then towards the end of the semester, we were able to do the data collection and data analytics fairly quickly.
All tests have inherent risks. Here are the ones for our project, which we thought were pretty relatively low, but worth considering nonetheless. Parts breaking under heavy tensile load from the load frame. We have the mounting fixture, which to prevent this, Dan did a FEA calculation in SolidWorks. Webbing of the straps, which we determined were strong enough for this test, and the forces applied, being that the bindings are only at a maximum of 10 DIN. Ski bindings themselves and the load frame itself, as well as sudden binding release, maybe sending things flying around the room. To prevent this, we had PPE on and PPE glass over the front of the load frame. And in addition to this all, we had mandatory lab safety training.
Looking at the results for the test, as you can see on the left side, as an actual axial test pulling up lateral release force. As you can see, it's quite a high steep slope rate for load versus extension, and then a sudden drop as it pops. The torsional is not so steep. As you can see, it slowly ramps up and then kind of levels off. And we're looking for the max release force there. It's not as defined as the axial, but it give you a pretty good metric. And that's only because when you're pulling up on a lateral, there'll be an actual pop for the binding versus torsional where there's a slow release of the binding. There were multiple, almost 20 for up and down scale for those tests. And we just collected the max release force for each one and then plot it on a scatter plot. As you can see, the axial and torsional data in front of you. And we did upscale, downscale, and multiple tests for each one. The trend, as you can see, the trend is quite linear for both axial and torsional, with the axial having a little higher slope. Then using these values, we then calculate the torque applied to the toe and heel bindings using a standard set by ISO. Is kind of the force versus length or torquing length. But ISO has a set length that they usually use. We did this mainly because ski shops use this standard. They really use a winter stagger machine to get these to calculate these values for them. But using our method, we took our force values using the ISO standard and then convert them into the forces.
So that being said, what did we find? So we're going to circle back to the first question of, are these bindings actually safe? And the answer is yes. We were able to predict a trend in the release force versus, well, for the pin setting versus your standard alpine settings. Even with, like I said, even with DIN setting using alpine adjustment methods, the results for tech bindings are fairly accurate with those alpine expectations. So our results were very close to what we expected for an alpine binding if we were to do the same test. So that being said, all in all, there's no increased risk of knee injury when using tech bindings. However, there still is a risk, so be careful. It's not all good. There was always some error and uncertainty in any kind of experiment. So a couple of the biggest things we saw was the strap slipping from underneath the ski boot. And this could be because it got caught in something, and as soon as it underwent loading, it just caused some jumps in our data. None of that really affected, well, to our knowledge, our data that drastically, but it is something to consider. Another thing that we noticed is that our load frame sample rate was lower than we would have liked it to be. We realized that if we increase that, we'd be getting a much smoother curve instead of something that is jagged, and our results would be more accurate. On the human side of the error, in calculating the torque, we had to measure our boot sole length and length to where the load was applied. So there is some variability there. And then precisely setting the DIN. Like I said before, there were two DIN measurements. There's our pin tension and our pivot tension. DIN tension, we found that uncertainty to be plus or minus half a DIN, whereas our pivot tension, we couldn't measure. So we had to actually measure the number of turns that we used for that set screw in the back. And then proper binding setup. The load frame is only going to read accurate data if it pulls directly up. We believe that we did with the setup that we used, but it's always going to be off by a little bit. So once we had our data, we did some actual hard calculations of this error using a hysteresis error, linearity error, repeatability error, and then obviously total uncertainty. And we found that there's a little bit more error in the axial tests and less error in the torsional tests, but both have a little bit of error. And like Jake said, using a winter stagger machine that is designed for this type of test, we expect that error to be reduced.
So in the future for this project, we could certainly improve on it in many ways. One of these being testing boots with different sole lengths, which could affect the release torque just based on the length, the force times distance. Next is maybe using a load frame with force over time instead of extension over time. That would give a more accurate reading of the force actually required, as opposed to just hoping that it would read properly on what we had now. And then it's testing different bindings, whether this be with a higher DIN limit. Ours only went up to 10, but they certainly go higher than this, so that'd be interesting to see how they test with higher DINs. And also using bindings that are ISO certified, which ours were not, unfortunately. Just that would kind of ensure the validity of the test. And then also, lastly, simulating the impact from the side and bottom of the ski and see how that affects the release force as well, which could also vary depending on the surface conditions of what they're skiing on. And our group would like to thank Professor Hoover, Todd Mull, and Jacob Weller in their assistance in this lab in this process. Their help was tremendous throughout the entire process, and their feedback really helped with developing our tests and helped using the equipment effectively.